Place you on listen only. You hear music until it begins.
Proper registration. Please all requested information slowly and clearly. With spelling, please state your first and last name. Follow. With spelling, please state your affiliation, followed by the pound sign.
Thank you for holding. Please continue to stand by. We will start in about 2 more minutes. Again, thank you. Please stand by. We will have music until we begin momentarily. Welcome and thank you for standing by. Participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star 1 on your touch-tone phone if you would like to ask a question. Today's conference is being recorded. If you have any objections, you may disconnect at this time. And now I'd like to turn it over to your host, Ms. Ellen Gray. Thank you so very much. You may begin.
Hello, and welcome to the media briefing for the Submesoscale Ocean Dynamics Experiment, also called S-MODE, currently taking place off the coast of California. My name is Ellen Gray with the NASA's Earth Science News team. You will be able to view the briefing slides by going to nasa.gov/live and clicking on the link above the audio stream. The slides are available as PDFs at the bottom, which you can view in your browser. After both presentations, we'll open the floor to questions. And without further ado, I'd like to introduce our first speaker, S-MODE Principal Investigator Tom Farrar from Woods Hole Oceanographic Institute.
Hello, everyone. My name is Tom Farrar. I'm the Principal Investigator for S-MODE, the Submesoscale Ocean Dynamics Experiment. So I'll be speaking to my slides that you can download from the webpage, and the first slide just lists some of the main people in S-MODE and institutions. We have more than 10 universities and research centers from around the U.S. involved in S-MODE. On the second slide, I just lay out some of the basic points about this experiment. So this is a NASA Earth Venture suborbital investigation. Suborbital means that it's, on planet Earth and not from space. So we're doing it with aircraft, remote sensing, and ships and robotic ocean vehicles. The program is focused on studying the role of what are called submesoscale ocean eddies in ocean dynamics. I'll explain more about what I mean by submesoscale, but it really just means scales from 1 to 10 kilometers. And I'll show you some examples in a moment. These eddies actually have a surprisingly important role in setting the exchange of properties between the atmosphere and the ocean, so things like heat and gases. So S-MODE will have 3 campaigns. We're having what we call a pilot campaign right now. That's a sort of scaled down version. It's still quite a big experiment involving 2 aircraft, a ship, and more than a dozen, actually almost 20 robotic autonomous vehicles. And then we'll have, starting in a year, 2 more intensive operations periods, so 2 month-long campaigns starting a year from now. The study region is offshore San Francisco. Now, if you'll go to the next slide, I'd like to explain more about what I mean about submesoscale ocean eddies. One of the first good views that we got of these 10-kilometer and smaller scale ocean eddies was from the Apollo 7 spacecraft, from photos that astronauts took of Earth on that mission. And we observed these spiral eddies that you can see in the sun glitter from the sea surface. We see them because the eddies are moving around surfactants on the sea surface, which affects the roughness of the sea surface. And then in the reflection of sun glitter from the sea, we see these variations. And you see these spiral eddies with a scale of 10 kilometers or less. That was of some interest, and later in 1984, NASA flew the first oceanographer astronaut, Paul Scully Power, and he was most impressed by the fact that these eddies that we call submesoscale are almost everywhere in the ocean. They're far offshore, they're in coastal zones, and I put up a quote on slide 4 from him and some more images. These are, again, photographs of the sea surface. This slide is showing an image from the Mediterranean Sea. But he said, even far from shore, you continue to see these spiral structures. Maybe the whole ocean is like this. I don't know. Over the last 20 years or so, we've come to realize from numerical simulations that they really are everywhere. So now moving to slide 5, I want to explain why they've been hard to measure. These eddies, they evolve rapidly, like their whole life cycle is a couple of days. They span 10 kilometers or so, and they get swept around by large-scale ocean currents. So on the one hand, they're too small for most satellite measurements, but on the other hand, they're too short-lived and too large to be easily measured by ships and conventional measurements where we actually put thermometers in the ocean to measure temperature, for example. So at the same time, now if we move to slide 6, I'm showing some computer model simulations of the ocean. And over the last 20 years or so, our ability to simulate these small eddies has far surpassed our ability to measure them directly. And through the work of these people running computer simulations of the ocean, it's become clear that these eddies really are widespread throughout the global oceans and that they have important effects. You can see in these simulations, this is ocean surface temperature and salinity offshore of California. For scale, I've marked San Francisco in the left-hand panel. You can see just tons of these eddies that are sort of 10 kilometers in scale or less, and you can see that they're stirring around the ocean, and they have this effect of mixing dense and light water. The density of the water is basically controlled by the ocean temperature and salinity. So these eddies are stirring up the water, and they're moving the water around so that the light water ends up on top of the heavy water, and that affects the upper ocean stratification near the surface, and then affects the heat and gas exchange between the ocean and atmosphere. And we found that these eddies have a really important effect over long time scales on the Earth's climate by modulating this air-sea heat exchange. So if you move to the next slide, I have a cartoon depiction of NASA's effort to make a big push to measure these eddies at a new level of detail. And the idea of S-mode is to test the hypothesis that these kilometer scale eddies make important contributions to vertical exchange in the upper ocean. And to do that, we've assembled a large team of scientists from all over the United States and even some international collaborators. And it's a really exciting effort. We have remote sensing of ocean surface currents and ocean surface temperature, ocean color, and other properties from aircraft, and a fleet of robotic vehicles and a research vessel. And they're off the coast of California right now making measurements. If you'll move to the next slide, we're showing here a map of sea surface temperature measured from satellite. The slide says S-mode study area is west of San Francisco at the top. And so these are measurements from satellite based on measurement of infrared radiation from the sea surface to estimate the sea surface temperature. And you can see that there are these swirling eddies, and the white polygon there is showing the S-mode study region. It has a weird shape like this because there are aircraft warning areas north and south of that polygon that are kind of reserved for use by the military. So this white polygon is a good place for doing aircraft-based work. We're about 100 miles offshore of San Francisco, and if you'll move to the next slide, I have some photographs from the campaign, actually. In the upper left is a sail drone, which is a robotic sailing vessel that sailed, 5 of them left San Francisco, went under the Golden Gate Bridge and out to sea, and have been making measurements all through the campaign of things like ocean velocity, temperature, salinity, and meteorological variables. On the right is the research vessel Oceanus on its way out to the site from Newport, Oregon. And you can see in the photo on the right a bunch of wave gliders. These are wave-powered vehicles that measure temperature, salinity, ocean velocity, and meteorological parameters. In the lower left is a white drifter, a disposable surface drifter. It's biodegradable. Excuse me, just a moment, please. There's someone knocking on our door. So on the, sorry about that. And then on the lower right is a ocean underwater glider that changes its buoyancy to sink and float. And as it does that, it uses wings to propel it forward and maneuvers around. And there are 9 of those out in the S-Mode region right now. Now, if you'll advance one more slide, we have photos of the aircraft in the experiment right now. The first one is the NASA B-200 aircraft from Armstrong Flight Research Center. And this is really exciting because it carries a new kind of instrument for measuring ocean surface currents using a Doppler radar that measures the centimeter scale ocean waves. And from that, it can infer the speed of the ocean surface currents and their direction. And if you would go to the next slide, we have another aircraft that is in S-Mode right now. It's a Twin Otter aircraft carrying an instrument package developed by researchers at the Scripps Institution of Oceanography to measure ocean waves, the wave height and direction, and the larger scale sea surface undulations from the currents. And it measures other properties like sea surface temperature and ocean currents by an optical technique. And here you can see in the lower right, they actually just a couple of days ago passed over one of the sail drones and captured this image. Now to slide 12. This is another cartoon depiction of the measurement assets in S-Mode. And this kind of gives you a sense of how we're trying to operate the robotic vehicles in a coherent array and supplement that with measurements from the ship and aircraft to map out the full 3D structure of this submesoscale variability. And so finally, if you'll go to slide 13, I just wanted to sum up what it is that we hope to learn in the S-Mode experiment. So we're trying to measure the 3D velocity, temperature, and chlorophyll structure of these eddies. And the goals are to collect a benchmark data set that we can use to test the performance of these state-of-the-art computer simulations of the ocean and to get more directly insights into how these eddies affect the vertical transport of heat and nutrients in the upper ocean. So that concludes my presentation. The final slide is just some resources and contacts and information about the institutions involved. Thank you, and now I'll hand over to Nadia, the program scientist for S-Mode.
Thank you, Tom. I'll let you take a second to open the slides on the website that Tom was pointing you earlier. I'm on the slide 1, title page. My name is Nadia Vinogradova-Schiffer. Hello. I direct Ocean Physics program at NASA headquarters, Science Mission Directorate. S-Mode is part of my science portfolio, and I'd like to zoom out a little bit from Tom's presentation and talk about how S-Mode mission contributes to NASA ocean physics and climate science that we do at NASA. Next slide, please. Slide number 2. S-Mode is joining a large, happy, and a healthy family of NASA's Earth-observing missions. And when we talk about NASA missions, we often refer to satellites. Here they are on your screen, our satellite fleet, the largest in the world, very comprehensive, and a very busy plot. And a large number of those satellite missions are dedicated to observe our oceans. They sort of take those vital signs, just like at your doctor's office, your temperature, pressure, ocean mass, ocean height or sea level, frozen ocean or sea ice, winds over the ocean, ocean color or its biology. So all of those are direct indicators of how the system is doing, how healthy is the Earth, and how healthy are our oceans, and how do they respond to a new climate that we now live in. Okay, so that's the satellites. So where is Azimuth on this chart, and how do we come in? And Tom already briefly mentioned it, that another unique aspect of NASA is that in addition to orbital assets like satellites, we also invest in suborbital missions, right? So missions that collect data from well below the orbit by an aircraft or research vessels or autonomous drones. And those suborbital missions are designed and executed by the members of the science community. So rather than directing a mission to a NASA center, any U.S. researcher can become a NASA mission scientist, at least for a few years. Those missions are competitively selected and endorsed by their peers, by their fellow scientists. So it's very prestigious to lead such a mission, which is what Tom is doing. And leading Azimuth in particular is a particularly important task because we at NASA have high hopes for this mission to demonstrate what the future of ocean physics from space might look like. So no pressure, Azimuth. But what do we mean by that? Let's look at a few examples on the next slide. So if you advance to slide 3, I'm on slide 3, and I hope you're too. So something that we at NASA already do well, after all, we've been in business of Earth observing for more than half a century. So what we do well is we collect a number of direct evidences of many major climate change processes. For example, warming of the planet, ocean heating, melting of the cryosphere, sea level rise. The plot on the left is one of such examples of our direct sea level measurements from NASA satellite altimeters. Today, we see that the seas are higher than they were 30 years ago. They continue to rise, and they rise faster. We also know that some of those changes are here to stay for a very long time. I'm talking millennial timescales. And it seems that perhaps another 0.5 meter of global mean sea level rise by the end of this century is inevitable. And whether it's more than 0.5 meter, it's up to humanity to choose. Including, from new agreements to be made next week in Glasgow at COP26, Climate Summit. So anyway, another direct observations of changing climate that I'm showing on your plot is measurements of ocean salinity, which we also do both using satellite asset and the Azimuth measurements that Tom already mentioned. And one of the aspects of salinity data in particular, its linkages with a changing water cycle, mostly because salinity is very sensitive to the amount of fresh water that comes in and comes out of the ocean. And having those direct measurements is what allows us to kind of dive deeper into the system's physics and ultimately improve projections of future climate. And the plot on the right illustrates one of such examples and showing you projected precipitation patterns in precipitation by the end of the century. You might notice a general tendency of drying of some already arid subtropical regions, which are shown in brown colors, and already wet areas such as tropics or high latitudes or storm track regions would receive more precipitation by 2100. So those of us on the East Coast, I guess we better get used to the wet and rainy day like we have today, recovering from the storm. So, okay, so those were a couple of examples of NASA's direct measurements, both from satellite and Azimuth. But what about something that we never measured before? Let's take a look at the next slide. I'm on slide 4. What we cannot measure directly, at least now, is how the ocean actually moves. So rather what we do, we actually derive or compute ocean circulation using our best knowledge of physics, mostly using geostrophic and hydrostatic principles. So here's an example of the derived ocean circulation based on the integration of billions of ocean measurements with a modeling framework, which we call ECHO. And ECHO stands for Estimating Circulation Climate of the Ocean. If we had a video call, you would actually see the movement of water, ocean currents, big ocean gyres, small eddies. It's actually quite mesmerizing to look at. And in fact, ECHO ocean circulation was featured this year during the announcement of the Nobel Prize for Physics. It's a proud moment for the climate community and NASA. So what ESMOD is doing, or one of the things that he's doing, is exploring and testing if NASA can figure out how to measure ocean movement from space, rather than just computing and deriving it from other measurements. So having those direct measurements would really revolutionize the way we do climate science or predict the weather. Because when the ocean moves, it obviously moves a bunch of properties with it, right? Properties like heat or energy, mass, salt, carbon, nutrients, phytoplankton, or oil spills, pollution, plastic, or you name it. So observing ocean circulation directly from space, meaning global coverage, that would be a huge leap towards the future of Earth science. And ESMOD is the first step to make such a future mission a reality. That's a big task. All right, next slide, please. That's not all that ESMOD can do. So as you might remember, Tom mentioned ESMOD ability to measure 3D velocities, meaning that in addition to knowing how the ocean moves horizontally, we also want to know how the ocean moves in vertical. This is how 3D comes from. So vertical motion is another key element that drives Earth's climate system. And it's even more difficult to measure directly, including measurements from space. But it is the movement in the vertical that drives the exchange between, let's say, the ocean and the atmosphere. This is what makes those Earth fundamental cycles work. Heat cycle, freshwater cycle, carbon cycle, moisture, momentum. On the left, on your figure on the left, on slide 5, it's an example of how the ocean is exchanging CO2 with the atmosphere. The blue colors are regions where the ocean is absorbing CO2, so it acts as a sink of atmospheric carbon. And red colors are ocean regions where the ocean acts as a source of CO2, so it's outgassing carbon to the atmosphere. So this ability of the ocean to absorb and store carbon is a tremendous help in slowing down the full impact of global warming. Well, still, over the past 200 years, atmospheric concentration of CO2 doubled. So today we know that it is higher than at any time in at least 2 million years. So as much as the ocean is helping, it's clearly not enough to maintain a balance. So that was the exchange at the surface, right? And in addition to that, another ESMOD mission goal is to understand the exchange between the surface and the subsurface waters. So, and an example of why it matters can be illustrated on ocean's ability to sequester heat in addition to carbon. And sequestering heat, absorbing and storing heat is another way how oceans slow down the full impact of global warming. We know that over the past 30 years or so, the ocean accumulated enormous amount of heat, as you can see on your figure on the right. Right? For context, in 1 year, ocean absorbed a few zetajoules of heat, which is, just comparison, it's 10 times larger than the energy consumption of all human population. And over the past decade, ocean amassed hundreds of those zetajoules. And I'm just noticing that the y-axis is mislabeled. That should be tens of zetajoules, so 10 to the power 22. In any case, ESMOD mission will help us understand those vertical velocities and transport processes, either it is heat or salt or carbon. And if ESMOD was not already awesome enough, there is the third novel aspect that ESMOD brings to NASA and ocean observing. It's the aspect of how does small scale matter for big, large scale climate processes. Let's go to the next slide, please. I'm on the slide 6. So NASA, together with CNEST, is launching a new mission next year called SWOT, which stands for Surface Water and Ocean Topography. It will measure all surface water on Earth, in the ocean, in the lakes, in the rivers. We are very excited about this new mission, which was, as I understand, was decades in the making. So for the oceans in particular, we, science community, are really getting ready to be blown away by this unprecedented resolution of the new SWOT measurements. And for the first time, we would be able to observe those small but very energetic features like ocean eddies, filaments, fronts, and we suspect that those small-scale features play a very prominent role in Earth climate, including processes that we covered earlier: exchange of carbon, heat, energy, moisture between the ocean and the atmosphere, or how do eddies help communication between the surface and below the surface ocean? How do this eddy help storing away those extra heat and carbon that we keep pumping into the atmosphere? Or maybe what is the role of those eddies and what would be the role when they play when ocean starts releasing this heat back? You know, just like your tea kettle will eventually boil. So when you have this new information from missions like SWOT, it is important that we have tools and knowledge to validate it, right? To distinguish between the noise and the signal, to interpret the physics that we have never seen before. That's where ESMOD comes in, once again, to help us interpret the physics and dynamics of the small-scale ocean features that we will observe in SWOT and potentially other future NASA missions. Because if we understand what we see, if we can interpret it in a meaningful way, we can improve our projections of the future climate, whichever it might be. And ESMOD helps us accomplish it. And so with that, and for my next and last slide, I would like to thank ESMOD team for their dedication, passion, and resilience in planning and executing the first campaign in a series of campaigns. So between the COVID-related delays, the scheduling issues, power outages, and now weather, including the cyclone that bombing teams on both East and West Coast, the team really keeps moving forward, very energized, and excited to see something new for the first time and learn about it. It's a true NASA spirit. Go ESMOD. You can follow the campaign at the link below. Thank you, and we are ready for questions if you have any. Ellen, back to you.
All right. Thanks, Nadia. Thanks, Tom. That concludes the presentation portion of the briefing. I'll now turn it over to our operator, Fran, to take your questions.
And thank you for that. If you would like to ask a question, please press *1. Please unmute your phone and record your name clearly when prompted. Your name is needed to introduce your question. *1. One moment, please, for our first request. If you would like to ask a question over the telephone, please press *1. Thank you. Our first question is from Allison Gatlin with Antelope Valley Press. Ma'am, your line is open.
Thank you. Hi. I guess I'm kind of trying to figure out what the timeline is for this campaign. I understand that part of it, at least, was happened earlier this year, and I'm wondering, is it still ongoing, or when are you out there flying, and when are the ships and drones at sea?
Sure. So we're out there right now. The ship is at sea offshore of California. In fact, if you want to see their position in real time, the web link on Nadia's slide will lead you to eventually, you might have trouble finding it, but you could see all the positions of all the assets right now. Right, so earlier this year we did a sort of what we call a pre-pilot campaign. We basically did some flights with some of the wave gliders underneath to work some of the bugs out of our instruments, you could say. And then now, starting October 19th, the ship set sail from Newport. They went down to the area. They actually went into San Francisco during the passage of the worst part of the atmospheric river event. There were 11-meter waves registered in our study region, so that's over 30 feet. And they went into also the ship was getting really beat up in the waves and was having some mechanical issues. So they went into port in San Francisco, waited out the worst of the waves and went back out. Let's see, they set sail on Wednesday and they've been working out there since. And the flights, everything will continue until around November 7th.
Okay. Thank you very much.
Sure. Thanks for the question.
At this time, I have no further questions in queue.
All right, we'll wait a moment in case there are other questions, maybe another minute or so. One thing to note, beneath where the PDF slides are on our media resources page, we have a link to additional B-roll and photography that is available for download in high resolution. All right, if there are no further questions, this will conclude our briefing. Thank you all for coming.
Again, conference is now concluded. Thank you everyone for your participation. You may please go ahead and disconnect.